Hi everyone, this is Mr. Wells, and I would like to do a quick little review of circular motion here. So let's imagine that we have somebody swinging like a ball on the end of a string, and that string is going to end up making a radius that the ball is going to be moving in. So the first question is, which direction is the velocity of this? And since you have previous experience in physics, hopefully you remember that the velocity vector, and let's assume that this is going in the counterclockwise direction, would be the velocity vector is tangent to the circle. So because of that, the velocity is sometimes called the tangential velocity, or sometimes the linear velocity, because we're talking about that. And so sometime later, this ball would be over here, and the velocity again would point tangent to the circle. And it can be shown, for example, if the string is cut, the ball then has no force on it and it moves off in a straight path tangent to the circle. So hopefully you've seen that before. But I also want to bring up something that you may not have discussed before, and that's the fact that this is going to kind of sweep out an area here. Okay, so as it goes around in the circle, it's going to basically, you can imagine the radius sort of sweeping out an angle, and so sometimes we talk about the angular velocity. And the angular velocity is going to be it's signified by the small Greek letter omega, and that's the number of radians per second that it sweeps out. So that's omega. The tangential or linear velocity is usually just v. Sometimes you'll see a subscript t on there, but not all that often. And that's going to be usually in meters per second. So one question is, how do these relate to each other? Well, let's think about one full revolution around here. So if we talk about one revolution, then I know the tangential velocity is the distance that it's covered, the number of meters that are covered, is the circumference of the circle, which is 2 pi times the radius. Okay. And the time it takes is, I'm just going to leave that as t. I know the angular velocity. One circle sweeps out an area of 2 pi radians. Okay, so that would just be 2 pi radians over t. So what you can see is they're nearly identical. We can easily come up with this relationship. You can see just by inspection here that the linear velocity is equal to the radius times the angular velocity. So that's a concept I want to bring up here. I'm sort of introducing this a little bit. We won't see angular velocity very much yet, but in the future it's going to be an important concept. So I just wanted to show that to you there. So that's how those two velocities relate to each other. Now, circular motion is often repetitive. Things keep going around and around and around in the circles. So we want to give an idea of how often this repetition occurs. So there are two terms to help us describe that. One is the period, okay, and the period is the time for one complete revolution. or you can think about it this way in terms of the units. That's seconds per revolution. And the symbol we use for period is capital T. So T relates to time. Capital T is a special time. It's the period or the time for one revolution. The frequency is the basically number of revolutions per second. So if you think about it, frequency, how often does it happen? Well, it happens 10 times a second, or it makes the circle 3 circles per second. That's a frequency. So the units on that would be seconds per revolution. And so if you look at it, it's, excuse me, I just did that backwards. Yeah, it's revolutions per second. So if you look at these, you can see that basically they are inverses of each other, okay, or reciprocals of each other. Seconds per revolution compared to revolutions per second. So there is a relationship between these two. So the period is equal to 1 over the frequency. Or you can say, very obviously, if mathematically works out this way, the frequency is equal to 1 over the period. So at this point, period is going to be the most often used rather than the frequency, but you'll see both sometimes. So the velocity of the object is often written in terms of the period. Okay, so we talked about the velocity, and I'm talking about the linear velocity. We said was equal to 2 pi r, and that is over the period. The time it takes to go around once is the period. Okay. So that's the idea of circular motion. Now, we know, getting back to this direction idea, if we go and take a look back this, that even if this is going at a constant speed, a constant number of meters per second, the velocity vector is always changing directions. And so we know that if something has a changing velocity, it must be accelerating. Okay, so something that is moving in a circle is accelerating. Okay, and the acceleration is often called the centripetal acceleration. And the word centripetal refers to the direction of the acceleration. So I believe it comes from the Greek. Centripetal means center seeking. So the acceleration points toward the center. And I'm not going to go into a detailed explanation of that. But if you do a little vector math, I believe in class I showed this once earlier actually when we were talking about vector addition. So the centripetal acceleration would have the same direction as the change in velocity. So if we had this velocity vector here, plus the change in velocity would add up to that vector, and you can show that it points toward the center of the circle. It may not be obvious, but it can. And you can also show that there's a relationship there in terms of mathematically finding it. And I'm not going to go through the derivation for you. So we use small a for acceleration. We often put a little c under there for centripetal acceleration. And trust me, and I know there's a derivation in your book, that is equal to v squared over r. So that's a helpful thing. And I could also write this in terms of, if I substitute the velocity that we have in here in for the velocity in that equation, you can see that I'd have it, I'm going to write it as 1 over r times v. If I substitute in 2 pi r over the period, and I square that, you're going to end up with, on top, I'm going to have a 4, 2 squared is 4, pi squared. I have r squared on top and r on the bottom, so one of those r's cancels out over the period squared. So that's another formula that's kind of helpful. It's not so much about memorizing it. It's nice to know that you can derive that relatively easily. I should put my subscript C there. Okay, so if something is accelerating, we know that Isaac Newton told us that there must be a force on it. So if this thing has a velocity in this direction, if you think about it, as it's moving around the circle, remember objects naturally want to go in a straight line at a constant speed. So this object wants to go in a straight line, and we have to basically pull it away from that straight line. And if you think about that, or the object on the string, the force is going to be in toward the center of the circle. So the force is going to be in toward the center, and we often call that the centripetal force. Another way to think of that is that the net force and the acceleration always have to point in the same direction. So basically, here, I'll write this down. Toward the center of the circle. So that's the way that the net force points. And that's why we call it the centripetal force. Okay, so for uniform circular motion, Newton's second law, we can think of Newton's second law in its most general form. F net is equal to ma. So for circular motion, the net force has to be pointed toward the center of the circle, and we can write this very often. We can think of it as the centripetal acceleration, and I could also write it as mv squared over r. And you could also write it in terms of the period and r by substituting in that equation that we just did a little while ago. Okay, so let's look at this in action. So let's say we have a student swing a rubber stopper around on the end of a string. Okay, makes a vertical circle. And so we've got the mass of the stopper. We know the radius of the circle is 0.3 meters, and it takes 0.25 seconds to make one revolution. And so my question is, what is the tension on the string when the stopper is at the top of the circle? Okay, so there's a string there, it has a radius. We know that tension is pull, so it's going to be down. So just like we always do, I'm going to draw a free body diagram of the stopper. So if that's the stopper, let's think of the direction, the forces on the stopper. So it is going to have a weight force acting down. That is, of course, going to equal its mass times little g. And there's going to be also a tension force. I also know sometimes it's good to specify which direction the acceleration is if you know that. So the acceleration is downward, so that's going to help me keep my signs straight. And so when we do this, in general, I know that for circular motion, F net is equal to the mass times the centripetal acceleration. So if I look at F net in terms of the forces on my diagram, I've got the tension plus the weight force equal to mg has to equal the mass times the centripetal acceleration. So that's going to equal m times v squared over r. Now I know that v is equal to 2 pi r over the period, so I can do a little substitution here. Excuse me, that's a plus. So the tension plus the weight force is equal to m over r. V is 2 pi r over the period. So T plus mg, when you do your canceling, is equal to 4 times pi squared times the mass times the radius over the period squared. And now I'll start working over here. When we have this, I didn't even realize this. I've got two capital T's in here, one for period and one for tension, and that is really difficult. So I'm going to, let me just call that TEN for tension. I don't want to confuse anyone with the notation. So this capital T and this capital T are very different things. Okay, so the tension is going to equal, if I solve for that, it's going to equal 4 pi squared m times r over the period squared minus little m times g. And if you do that, I'll trust that you can trust me with the math. I did this earlier, substituted in 0.04 for the mass, substituted 0.3 in for the radius, and substituted in 0.25 for the period, because that's the time it takes to make one revolution. You get an answer to two significant digits of 7.2 newtons. And I'm trusting that you'll check my math on that. Okay, so the second one is with the string at the bottom. So you notice the string at the bottom, okay, the tension is now going to point up. So what's different is our diagram. So now we have a tension force up, and I've got the weight force, mg, pointing down. So it's a very, very similar problem, except that when we write F net, we're going to have the tension force minus mg, okay, because the acceleration here is in this direction. So the tension force is going to be considered the positive direction, and the weight force is going to be considered the negative direction. So the tension force minus mg is going to equal this stuff on the other side, which I'll just write as 4 pi squared m times the radius over the period squared. And what you'll see is that when you solve that, similar to what we did before, all the numbers are the same. The tension ends up being 8.0 newtons. So it's greater at the bottom, and if you think about it, it kind of makes sense, because at the bottom it's holding up it's got to balance out the weight and have even more force to keep it turning in the circle to produce that change in direction. At the top, the weight is helping to produce that change in direction a little bit, so they don't need quite as much tension from the string. Okay, well, I hope this provides you a nice review about the about uniform circular motion.